Hello everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. In today's video we're going to describe the fundamental theorem of the algebraic calculus. This follows on from our fundamental formula of the algebraic calculus that we've just been talking about. This is a formula that tells us what the signed area of a particular kind of polynomially parametrized curve is. A curve given by two pure powers, alpha to the m and alpha to the n. So that generates some kind of curve. For example, this is an example, a very simple one, where the curve is alpha squared, tracing out the curve we usually call y equals x squared. And what we have here is the signed area from 0 to 1 of this curve, expressed in terms of these powers m and n. And the answer is, it's n minus m, the difference here, divided by 2 times n plus m. The difference divided by 2 times the sum. And geometrically, it's giving us the signed area of this region formed by a part of the curve where the parameter goes from 0 to 1 and the line that we get by going straight back. That red area there, that's the formula for it. So in general, we have a curve gamma which is PQ, where P and Q are polynomials. This is a polynomially parametrized curve, and these are exactly the Casteljau Bezier curves that figure prominently in the analysis of modern curves these days, in graphics and so on. So these are exactly the curves that we can obtain a solid integration theory for. Now, what we want to do today is to generalize this, to extend it, so that it's not just a specific formula having to deal with these very particular kinds of curves, but something that's more general. And this fundamental theorem is going to be both theoretical and practical, and will also have a geometrical aspect. So it's an absolutely core theorem for our subject. So let's have a look at how we can use that fundamental formula to obtain integrals for more general polynomially parametrized curves. For example, this one gamma here, which is 1 plus alpha cubed, 2 minus alpha plus alpha squared. That's a curve that looks something like this in blue there. And we're interested in just the piece of the curve going from 0 to 1. So when the parameter is 0, we're at the point 1, 2. And when the parameter is 1, we're at the point 2, 2. So just talking about that little segment of the curve. And that segment of the curve will bound a region where we're looking at it from the origin. That's always what we do here in this approach to the algebraic calculus. So we're interested in getting a formula for that area there. So how do we do it? How do we use that previous formula? Well, we use the linearity, or actually more precisely the bilinearity of the situation. The fact that we can break this thing up into a lot of little formulas, each involving pure powers. So how do we do that? So if we're interested in the signed area from 0 to 1 of gamma, then there will be 6 terms altogether corresponding to the 6 possible ways of combining the terms that are involved here. So there'll be a signed area from 0 to 1 of 1, 2, and then minus 1 alpha, plus 1 alpha squared, and then over here an alpha cubed with a 2, and then an alpha cubed with a minus alpha, and an alpha cubed with an alpha squared. So we have these 6 components, and the fundamental formula allows us to compute numbers for each one of those 6. And what are those numbers? Well, the first one here, this 2 could kind of be pulled out, and then it'd be just a 1 comma 1. And that's actually a special case because the power of alpha there is 0. This is really alpha to the 0, alpha to the 0. If we applied the formula without thinking too carefully, we would get the difference, 0 minus 0, divided by 2 times the sum, which is also 0. So we get 0 over 0, which is a bit problematic. So we're going to have to deal with that separately. And the way to deal with that separately is to realize that the special case when the 2 exponents are 0, s sub 0 to 1 of alpha to 0, alpha to 0, in other words, where we have 1, 1, that is 0, okay? So we don't really use the formula in this case, it's just going to be 0. And what about these other ones? Well, here we have an exponent of 0, and here is an exponent of 1. So 1 minus 0 is the difference, divided by 2 times the sum, which is 1. Over here, the exponents are 0 and 2. The difference, 2 minus 0, divided by 2 times the sum, 2. Over here, exponent of 3 and 0. The difference is 0 minus 3, divided by 2 times the sum, which is 3. And there's a 2 because this number here, 2, can by linearity be pulled out front. So we need to actually pull that out front before we have an alpha to the 0 in there. Over here we have a 3 and a 1, so we get 1 minus 3 over 2 times 1 plus 3. And over here, 2 minus 3 divided by 2 times the sum 5. So we've said this thing here is 0, and then here we get a minus a half, here we get a plus a half, here we have a minus 1, here there is a minus 2 divided by this, so that's plus 1/4 altogether. And over here we have minus 1/10, for a grand total of minus 17 over 20. So that's the signed area determined by this segment of this polynomially parametrized curve, obtained by just applying the fundamental formula to all possible constituents where we expand the integral by linearity. So we can do that, but we want a more general way of proceeding, something that's a little bit more efficient for this kind of thing. That's what the fundamental theorem allows us to do. So the key algebraic tools that we're going to need are Faulhaber's algebraic derivative and integral. These are operations that we've talked a lot about, the operation of d for derivative and s for integral. And what these are just formal operations or purely algebraic operations defined on polynumbers by these relatively simple rules. That d of alpha to the n is n times alpha to the n minus 1. And n here can be a natural number, 0, 1, 2, 3, etc. And s of alpha to the n is by definition alpha to the n plus 1 divided by n plus 1. So for the derivative, the exponent comes down as a coefficient and it's then reduced by 1. For the integral, sort of the opposite, the exponent is increased by 1 and we divide by the new exponent. And these two operations extend linearly to polynumbers. So for example, if we need to find the derivative of 3 minus alpha plus 4 alpha cubed, we just apply the d to each one of these terms. The derivative of 3 is 0, because that's alpha to the 0, so the 0 will come down and we'll get 0. Minus alpha, the derivative is just minus 1, and here the derivative is 12 alpha squared. The integral, on the other hand, the integral of 3 is 3 alpha. The 0 gets bumped up to a 1, and then we divide by 1, so we get 3 alpha. Then minus alpha squared over 2, plus 4 alpha to the 4th over 4. So the 4's cancel, we just get alpha to the 4. Okay, one more important thing to define is a kind of a relative integration where we're taking the difference between the integral's values at two numbers. So capital S from t to u of some polynumber p is by definition the integral s of p evaluated at u minus the integral evaluated at t. We're taking the difference between the Faulhaber integral at two different values. And there's no condition on the t and u. They can be any numbers. They don't have to be one bigger than the other. We just make a small observation, very simple, that the relative integral from t to u of p plus the integral from u to v of p is going to be the integral from t to v of p. Okay, so these are the ingredients that we're going to be using to formulate the fundamental theorem of the algebraic calculus. Okay, so here is the fundamental theorem of the algebraic calculus, or for us, just the fundamental theorem of calculus. For polynumbers p and q, the signed area from t to u of the polygonally parametrized curve p, q is equal to this number. This is a number. Okay, what is this? This is 1/2, first of all. And then there's a relative integral, the Faulhaber integral, from t to u of this polynumber. And what's inside? It's a combination of p and q together with the Faulhaber derivative. It's p dq minus q dp. P dq minus q dp. So p and q are polynumbers. This is another polynumber. We take that polynumber and we integrate it in the sense of Faulhaber, a purely algebraic integral, the S operation, from t to u. And then we divide by 2. So let's check that this actually agrees, at least, with the fundamental formula. If p happens to be alpha to the m and q happens to be alpha to the n, then what do we get? Then the quantity here that we're interested in is what? Well, there's a half. Then there's an integral from 0 to 1. And now we have to look at this expression. So p is alpha to the m. The derivative of q is n times alpha to the n minus 1. Now we subtract q, which is alpha to the n, times the derivative of p, which is m times alpha to the m minus 1. Now, if we look what's inside here, we see that the common power of alpha is alpha to the m plus n minus 1 in both of these terms. And the coefficient then is n minus m. So we have to take the integral of that. Okay, the n minus m is just a constant, so we can pull out of the integral. So we get n minus m over 2 out front. And then we have to integrate this pure power, alpha to the m plus n minus 1. And we know how to do that. That's Faulhaber's definition. So we raise the exponent, it goes to m plus n, and we divide by that new exponent. So we have an m plus n in the bottom. And then we're going to evaluate that from 0 to 1, and we use this kind of convention. We put square brackets with a 0 down here and a 1. That means we're going to evaluate this at 1, and we're going to subtract the value at 0. That's what the meaning of this relative integral is. Okay, what happens when alpha is equal to 1? In that case, we're going to get 1 to the m plus n over m plus n, so just 1 over m plus n. And when we substitute 0, we're just going to get 0. So this difference is just 1 over m plus n, and the total is n minus m over 2 times m plus n. So exactly the fundamental formula of the algebraic calculus. So this sort of more fancy theoretical formula agrees with our fundamental formula when we're talking about pure powers. All right, so we now want to prove this fundamental theorem. And that means we have to touch base with how we define the signed area to begin with, to ensure that the expression that we've written down actually does agree with our definition of the signed area. Okay, so to do that, let's define for polynomials or polynumbers p and q, numbers t and u, and the curve gamma, say, which is the curve determined by p and q. We're going to look at this expression here that occurs in the fundamental theorem, and we're going to give it a new name temporarily. S tilde from t to u of pq. That's by definition 1/2 of the Faulhaber integral, the capital S from t to u of p dq minus q dp. This is a small s, like a signed area, but it's like an alternate signed area, temporary signed area. Okay, what do we want to do? We want to show that this quantity here satisfies the 5 defining properties of the signed area, because we know that those 5 defining properties completely characterizes the signed area. So if this quantity satisfies the 5 properties, then it has to be the signed area that's involved in the fundamental formula. And I'm just reminding you what these various properties are. So the normalization condition, an additivity condition, the linearity conditions, a translation condition, and a dilation condition. So these are just the familiar things, what it means for this S tilde to satisfy these 5 properties. We want to prove that this expression satisfies these 5 things. So we have some work to do. So let's start with this normalization condition, and let's see why this S tilde 0, 1, this is here the definition, it's given by taking the P times dq minus q times dp, and the dp is 0, so we get 0 there. So we get S from 0 to 1 of just 1, which is alpha from 0 to 1, which is indeed 1/2. And the other one is the same story, you just get minus 1/2, you can check that. In terms of additivity, well, we need to check that S tilde from t to u of some curve plus S tilde from u to v of some curve is S tilde from t to v of that curve. Okay, why is that? Well, that's because this thing here, here's the expression for it. P dq minus q dp, and we're taking a Faulhaber integral from t to u. And then what about this thing? Well, it's the same thing inside, but now we're taking the Faulhaber integral from u to v. So we just use that elementary property of the Faulhaber integral, that the integral from t to u plus the integral from u to v is going to be the integral from t to v. So these things can be combined to get 1/2 of this thing, and that's the quantity S tilde from t to v of gamma. In terms of linearity, well, here's an example of that. Say you want to calculate S tilde from t to u of p plus r q. So here's what it looks like. The p plus r is there times the derivative of q, and then subtracting q times the derivative of p plus r. And then we use basic linearity here. So this is going to be p dq plus r dq. And we use the linearity of the derivative. The derivative of p plus u is the derivative of p plus the derivative of r. So this becomes that. And then we get a p dq minus q dp, and minus q dp, yes, okay, that one there, plus the r dq minus q dr from those two terms, again with halves out front. And then we recognize that this thing here is what we call S tilde from t to u of pq, and this one here is S from t to u tilde of rq. So that establishes the linearity, one of the three linear properties, and the other ones are similar. Now, to establish properties D and E, we are going to need two lemmas of independent interest that tell us what happens to the Faulhaber derivative operation and the Faulhaber integral S operation when we translate a polynumber or we dilate a polynumber. So let's start with the derivative. So for a polynumber p and some number c, here's what happens when we take the derivative of a translate. So if we look at the polynumber p of alpha plus c, that means wherever you see an alpha in p, you replace the alpha with an alpha plus c. It's like some kind of algebraic translation of p. And you take the derivative of that. The claim is that's the same as just taking the derivative of p itself and then replacing alpha with alpha plus c. And what about a dilate? Well, it's similar, but there's a little bit of an extra twist. So if you take the derivative of the polynomial p evaluated at c alpha, so now you take all the occurrences of alpha and you replace each one of them with c alpha. Geometrically, that corresponds to a rescaling or a dilation, but it's just a purely algebraic thing. So you take that, that algebraically modified polynomial and take its derivative. The claim is that that's c times the derivative of p evaluated at c alpha. Okay, so let me illustrate those. So let's look at p equals 3 plus alpha squared. There's a polynumber. And c, say, is the number 5. Okay, so the first thing, d of p of alpha plus c. What are we talking about? So this is now the polynumber that obtained by replacing the alpha with alpha plus 5. So it's the polynumber 3 plus alpha plus 5 squared. And what is that polynumber? Well, you can expand that out. That's 28 plus 10 alpha plus alpha squared. So we're being asked to take the derivative of that. And the derivative of this is 10 plus 2 alpha. Okay, good. And on the other side, d of p at alpha plus c. So what's the derivative of this thing? It's just 2 alpha. And I'm going to write 2 alpha in square brackets here, and then this alpha plus 5, because we're going to evaluate this polynumber at alpha plus 5. In other words, replace the alphas with alpha plus 5. So we get 2 times alpha plus 5, which is 10 plus 2 alpha, which is the same thing that we got over there. So these things are equal. These things are equal here. That's good. Okay, how about this one here? We'll use the same example. D of P of 5 alpha. So now we're taking the poly number and replacing alpha with 5 times alpha. Well, that's 3 plus 25 alpha squared. When you take the derivative, you get 50 alpha. And over on the right-hand side, what's over there? Well, there's a 5. That's the number we're dilating by. D of P of 5 alpha. So there's a 5. And now we're asked to take the derivative of P, which is 2 alpha, and evaluate it at 5 alpha. So it's 5 times 2 times 5 alpha. So we're evaluating this at 5 alpha. The alpha is replaced with 5 alpha. We get 2 times 5 alpha for a grand total of 50 alpha. And that's pleasantly the same thing as we got before. So yes, we can see that those examples explain or illustrate the theorem. And what about the proof? Well, you could do this by an explicit calculation because you know what the derivative does to pure powers. And it suffices to sort of do it one pure power at a time because it's entirely linear. But you could also try to use the chain rule to prove it. Okay, so that's an important ingredient to understand how the Faulhaber derivative is affected when we translate polynumbers or dilate them. And now here is the corresponding lemma for what happens to Faulhaber integrals when we translate a polynumber or dilate it. But it will turn out that it's simpler if we look at the relative version. What happens to the relative integral between two values when we translate or dilate. So here's the lemma. There's very corresponding formulas to the derivative ones. So the integral from t plus c to u plus c of p is the same as the integral from t to u of the polynumber p of c plus alpha. And in terms of dilation, the integral from ct to cu of p is again the constant c times the simpler thing, integral from t to u, but of p of c alpha. Okay, as an illustration, so here's a polynumber p, here's c equals 3, and here I've evaluated the left-hand side, you can check that. Here I've evaluated the right-hand side, you can check that, and they're equal. And for the same polynumber p and c, here I've evaluated this left-hand side, you can check, that's what you get, and here the right-hand side, and these two things are equal. So have a look at those numbers and make sure that you understand the calculation. In terms of a proof of this, well, it's again an exercise. In this case, probably the simplest thing is just to use linearity and prove it for alpha to the n. When p is alpha to the n, you prove it in that special case by actually making computation. And then you conclude that it's true for general polynumbers by the essential linearity of the Faulhaber integral. All right, so now let's return to proving our proposition. Remember, we still have these properties d and e to verify for this quantity s tilde from t to u of p of q, which is defined by this expression. So property d concerns translation. So what happens when we take s tilde from t plus c to u plus c of some curve pq? Okay, the definition is it's 1/2 the Faulhaber integral from t plus c to u plus c of p dq minus q dp. Okay, so what is that? Well, this thing here is an integral. Okay, so the integral t plus c, u plus c of something. By the previous lemma, we can transform that to a corresponding expression 1/2 integral just from t to u, but now we have to evaluate all of these things at c plus alpha. So it's p of c plus alpha times the derivative d of q at c plus alpha minus q at c plus alpha times the derivative of p at c plus alpha. And now we have to look at what happens when we take the derivative of something evaluated at c plus alpha, basically translating the derivative. So we have to look at the previous lemma that tells us what happens with the derivative and how it affects translation. So the point is that if you take the derivative and then you translate, that's exactly the same as first taking the translate and taking the derivative. So this thing here can be replaced by the derivative of the translate q of c plus alpha. Similarly, d of p of c plus alpha is the derivative of p of c plus alpha. So we can rewrite this to this. And when we do it then, we see that what we're really having is s tilde from t to u of p c plus alpha q c plus alpha. Because this here is just what you get when you take this thing and multiply by the derivative of this minus this thing times the derivative of this. And that's the property D that we want to verify. How about property E? Well, that involves a dilation. So we're looking at S tilde from CT to CU of PQ. Here's the definition of that. And now we have to replace this integral from CT to CU with just an integral from T to U. But if you look at the previous lemma, there's a constant of C that's introduced when you do that. Okay, and then we have to evaluate P at C alpha, and we have to evaluate this derivative D of Q at C alpha. To evaluate that at C alpha, we have to evaluate this derivative at C alpha. Okay, but this constant C now, because the integral is linear, it could be brought inside here, and we could multiply that C by each of these derivatives. Okay, so imagine multiplying that derivative there with a C and that one there with a C. And then you'd see that the other part of the derivative lemma that we just talked about allows us to replace C times D of Q of C alpha with just D of Q of C alpha. And replace C times D of P of C alpha with D of P of C alpha. And otherwise, the 1/2 and the integral are unchanged. And when we get to that, then we see that what we really have is S tilde from T to U of the new poly number P C alpha and Q C alpha. Because there's P of C alpha, and there's the derivative of Q of C alpha minus Q C alpha times the derivative of P of C alpha. So we've established that the E property also works. So all 5 properties are holding for this S tilde TU defined this way, defined using the Faulhaber derivative and the Faulhaber integral and this particular combination PdQ minus QdP. And also 1/2 thrown in for good measure, but we're used to that by now. Okay, so to wrap up, the quantities S tilde from T to U of P of Q defined this way satisfy exactly the same properties that our signed areas do, namely A, B, C, D, and E. And we saw earlier in a previous video that those 5 properties characterize the signed area. So if we have some other expression that satisfies the same 5 properties, then it's actually equal to our signed areas. That tells us that this expression here really is equal to the signed area of the curve PQ from T to U. That's the fundamental theorem of calculus. The signed area from T to U of PQ is 1/2 the Faulhaber integral from T to U of P dQ minus QdP. The Faulhaber operations D and S are enough for integration. Now I realize that this is a major departure from the usual story. You're going to have to think about this. This is a different way of thinking. We have not used any Riemann sums. There's no limits involved. yet we've somehow obtained this very important formula for calculating these actually more general integrals. Integrals of curves, not just integrals under functions. Okay, this is more general, it's more powerful. And it also, well, we'll see, it has a geometrical aspect. This is actually not so far from the original formula of a signed area of just a simple triangle. You know, x1, y2 minus x2, y1, the same kind of thing divided by 2. So it's a very important, a key theorem in the calculus, and sort of the theoretical side of the fundamental formula that we've already talked about. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.